We are finishing up with chapter 2 in this video. So this is the fourth video for chapter 2 and the last one. Yay for that. So falling objects. There's a wonderful YouTube video about things falling at the same rate if there is no air resistance. If you haven't thought a lot about falling, maybe this would be new, but Galileo is famous for coming up with the notion that an object in free fall falls at the same rate regardless of how heavy it is if there's nothing holding it back, so no air resistance. And there's some wonderful videos about this. I'll post a link on the assignment for this so that we can all look at it. All right, so what pulls an object down? Obviously, if you drop a ball, it falls and it hits the ground. And the reason it does that, of course, is gravity. Well, gravity is a name for that attractive force between any object on the surface of the earth and the center of the earth. Objects come together because of a gravitational attraction. Now, when we talk about gravity, we know that because it's a force that makes things accelerate. They go faster and faster and faster. And in fact, the acceleration due to gravity is symbolized by little g. It's a lowercase g, and it's equal to 9.8 meters per second squared, which is the same as 980 centimeters per second squared, or that is the same as 32 feet per second squared. We'll be using this a lot, so 9.8 meters per second squared will be a number you write down frequently. Galileo is really famous for sort of starting scientific inquiry. Before Galileo's time, if you were a physicist, you were called a natural philosopher, and you didn't actually do experiments, you sat around and thought about things. But Galileo was the first to really get involved and make things and do experiments. And so we think of him as the father of modern science. He was just a very fascinating person. So there is a demo with 2 pieces of paper. I'll again do that in a separate video. I found that I can't incorporate them into these Zoom videos, so it is what it is. Alrighty, so if everything falls with a constant acceleration, does that mean that as you go higher and higher and higher, so you drop a rock out of the first floor of Minji's, and then you go to the second floor and drop it, it's faster, excuse me, when it hits the ground. How about if we go to the third floor? It's faster. The roof, it's faster. Is the velocity unlimited? Well, actually, no. There is something called air resistance, and that usually puts a limit on the maximum velocity an object can have. We call that maximum limit its terminal velocity, and it is dependent on what you're falling through. So air compared to water compared to a vat of maple syrup, who knows what you're dropping things into. For a skydiver, terminal velocity is 140 miles per hour, which translates into 62.6 meters per second. So let's utilize dropping things and terminal velocity. Our question is, when will a skydiver in free fall reach terminal velocity? So again, we want to have our knowns, finds, and formulas. We want to start out with listing our formulas. You don't have to put them in a box. It was just easier for me. Again, this very first one, probably not necessary. I wouldn't even write it down. But delta x over delta t is v final plus v0 over 2. A is delta v over delta t, and delta x is v0t plus 1/2 a t squared. These 3 are important. So what do we know? So we know we've got a skydiver in free fall, and we want to know, when does he reach terminal velocity? So maybe the when is easier. When is, how long does it take? So we know we're trying to find a delta t. All right, what else do we know? We know that he's a skydiver. And again, please excuse the blue underline. I should have spell checked it, and that would have made it go away, and it didn't. So V sub 0 is equal to 0 meters per second. V sub 0 is 0 meters per second. How did I get that? It doesn't tell me that. Well, you think about it. You're in a plane and you're getting ready to jump out of the plane. Do you run from the back of the plane? Run, 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 run. And then dive out. No. If you were going to do that, they would have told you. Do you have a jetpack on? And are you cranking it up so that the minute you leave, boom, you're going to have some sort of big velocity? No. They would have told you if there was a jetpack. So we assume you get to the door opens, you take a step out. If you're going to do anything else, they have to tell you. So V0 equals 0. What else do we know? Well, we know we're talking about terminal velocity, so that's the ending velocity. We know our ending velocity is 62.6 meters per second. So we know that V final is 62.6 meters per second. Which way is it pointing? Down. You are falling. It's going down. So we have to indicate that. I do it usually two ways, with an arrow pointing down and the words. Why? Because the more reminders I can get of which way things are going, the better off. Velocity is a vector, and we have to keep up with the direction. What else do we know? Why are we going to go faster and faster? Oh yeah, there's an acceleration, and that's equal to gravity, and it's equal to 9.8 meters per second squared. So we know our acceleration is equal to 9.8 meters per second squared. Which way does it point? Acceleration due to gravity always points down. It points to the center of the earth. So I need another one of those down facing arrows and the word down beside it, because I need help. You don't have to do both. If you want to just do the words, that's fine. If you want to just do the arrow, that's fine. What else do we know? Well, we have to pick a direction for positive. Some people always make up positive, but I've told you that given a choice, if we're only moving in one direction, I make down that direction the positive direction. So the velocity is down, the acceleration is down. I'm going to make down our positive direction. If instead of jumping out of the plane and just going down, we had a trampoline and we'd gone down and up and down again, I might have made up positive and down negative. But we aren't doing trampolines, so down is positive. And again, you don't have to do that. You could make down negative if you wanted to. All right, now we have to pick a formula. And again, remember, we're never going to use this first formula, so I don't even bother to write it down most of the time. Delta x over delta t. Do we know a delta x? No. Do we know a delta t? No. Moving right along. A, we have an A. V final, we've got that. V0, we've got that. Delta t, we would like to know that. This is our magic equation. And again, if you can't see it just by going down the list, it's okay to write one down, plug in, discover you screwed up, put an X beside it, and pick a new one. So I know that A equals V final minus V0 over delta t. We can plug into it. We know acceleration, that's 9.8 meters per second squared. We know V final, that's 62.6 meters per second. We know V initial, it's 0 meters per second, and we are looking for delta t. This is the equation. We've plugged in everything. Now what? 62.6 minus 0 gives me 62.6. So I'm going to have 9.8 meters per second squared equals 62.6 meters per second divided by delta t. We need to get the delta t out of the denominator. Fractions are almost always our enemy, so anytime you can clear the fraction, anytime you can multiply both sides by it to get it out of the denominator or do any other kind of arithmetic to make it go away, the better off we usually are. So to get the delta t out of the denominator, because it is in the denominator, it's dividing into the 62.6, we have to multiply both sides by delta t. So to get it out, we want to multiply both sides by delta t. So the delta t comes up on the left. If I multiply the right by delta t, the delta t's cancel. And again, I've sort of skipped the semi-step. If you need to write it down, write it down. So to undo division, you multiply. So delta t multiplied by 9.8 meters per second squared equals 62.6 meters per second. But I need to move the 9.8. I want delta t all by itself. It is multiplied by the 9.8. To get rid of the 9.8, to undo multiplication, you divide. So I divide both sides by 9.8. That leaves me a delta t on the left, and the 9.8 comes over to the right in the denominator. And now we just do the arithmetic. So you have 62.6 divided by 9.8, which is 6.3877 seconds. That is probably too many digits to the right of the decimal. I would probably keep 2. I know our numbers only had 1, but I tend to err on the side of generosity when it comes to significant figures. So 6.39 seconds. Please do not round off excessively, and certainly do not round off early. All right. We're going to always pick a direction to be positive. So G can be positive or negative. It just depends. You can change the x's in an equation to y's if you're dealing with only vertical directions, if you want to. It's arbitrary. Objects in free fall have a constant acceleration, and that's because of gravity, but they have a changing velocity. I pick something up and I drop it. The minute you let it go, it starts out, it has a 0 velocity, and then it goes faster and faster and faster and faster. When it hits the ground, the velocity is not 0 at the moment of impact. If you believe it is 0 at the moment of impact, we're going to let you lie on the ground, and I'm going to drop rocks off the roof onto you, and you can tell us if they hurt. Now, I know no one will want to volunteer to do that. So, on impact, the velocity is not 0. It is 0 directly after impact, but not at impact. All right. So what else can we write down? So it's thrown up, the velocity changes, it goes up, 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 it stops, it comes down, down, down. It is important to know that at its peak, v is equal to 0, but the acceleration is equal to gravity, is equal to negative if we assume up is positive and down is negative. So during the entire time, if you throw something up and then it comes down, if you throw it up and then it comes down, during the entire time, the acceleration will be pointing down, so negative for us, but the velocity will change. Velocity and acceleration are not necessarily in the same direction. We have a little graphic from the book. So we're throwing things, the velocity goes up, 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 it slows down, 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 it stops, it turns around, it goes faster, faster, faster. So throwing it up and dropping and having it move compared to just dropping it. And you can certainly go back and look at this later. It's in your notes. All right, acceleration can be given in terms of multiples of little g, the acceleration due to gravity. Who cares about this? Well, actually, astronauts, test pilots care about this. when you are doing training at these really rapid accelerations, your body experiences what they call G forces. So the acceleration might be given in multiples of G. So 4G would be 4 multiplied by 9.8 meters per second squared, which gives you 39.2 meters per second squared. There's an example in the book. Again, this is the online version. And you'll want to go back and look at the 3 graphs, looking at position versus time and velocity versus time and acceleration versus time. Actually, I think we've talked about those. And then there are some homework problems to consider. And this stops our discussion. So chapter 2 is done.